Assalamualaikum warahmatullahi wabarakatuh. So this is the last part for the bulk deformation process, which is the wire and bar drawing process. So wire and bar drawing is a process where the cross-sectional of bar, rod or wire is reduced through pulling through a die opening. So this process is similar to the extrusion process, except that in extrusion it is push, but in this wire and bar drawing process, the work material is being pulled. Although drawing applies tensile stress, compression also plays a significant role in squeezing the metal through the die opening. This diagram showing the schematic diagram of the wire and bar drawing. So in here you will see there is draw die here. Okay, so this is the die opening over here, and this is angle, the die angle alpha, and then we are going to see that the diameter of the starting stock and the final diameter of the work. Okay, so in here there are also another component, which is LC, which is the contact length between the die and also the workpiece. So this is calculated by using LC equal to D naught, which is the initial diameter, minus the D final over 2 sine alpha. Okay, so it need the angle for the die. Here is the animation on how the process will take place. The workpiece will go inside here, and then it will be pulled. Okay, so then it will come out smaller in diameter compared to the initial one. Change in size of work usually given by the area reduction, okay, the cross-sectional area of the work part. So it is calculated by using R equal to A naught minus A final over A naught. So this one will be the reduction ratio, where the R is area reduction in drawing, A naught is the original area of work, and AR is the final work. Under the condition where no friction or redundant work occur in the drawing, the true strain can be calculated by using the epsilon equal to ln A naught over the A final, or we can simplify it equal to ln 1 over 1 minus R. Okay, so in here the stress for the ideal deformation can be calculated by using equation sigma equal to average flow stress times the strain. Okay, so then you'll get the equation like this one. Okay, so for the average flow stress, the equation is still the same. Recall back the average flow stress equation, which is YF equal to K epsilon N over 1 plus N. Okay, so as we discussed previously, friction is unavoidable in the process. There are many ways that we can do or we can propose to predict the draw dress, but here is the equation presented by the Shea. Okay, so the draw dress can be predicted by using this equation, where in here we are going to consider the die work coefficient of friction, die angle, and factor that account for inhomogeneous of the process. So the equation for all the part is given like this. Okay, so the D equal to D naught plus dF over 2, LC equal to D naught minus dF over 2 sine alpha, and the force is calculated by using area final time the draw stress. Okay, so then when we put it together, the equation inside the draw stress, then you will get this equation for the full equation. Although the process for wire drawing and bar drawing is almost the same, but the process is totally different and the different machine is used. Okay, the different mostly is because of the stock size. Okay, so the starting material of the bar drawing and also the wire drawing. Usually bar drawing involve large diameter bar and rod, okay, and wire drawing, of course, the starting material will be small and the final material also very small. The small diameter can go up to 0.03 mm, which is around 0.0001 inch. So although the mechanic are the same as mentioned, the methods, equipment, and even terminology will be different compared to the if you compare both type of process. For drawing practice, usually it is performed as cold working. Why it is called use cold working? Because usually it involves a very small material. So what happen is if you use hot material, okay, so the material is being heated. What happen is when it is pulled, there is possibility of necking. Okay, so for example, like there will be a thin area while the other area is still bigger. So in the end, this part that being thin will become snap after the process. Okay, so usually this process is frequently used for round cross section, and the example of the product, for example, for the wire, in terms of a wire, you can produce electrical wire stock for fences, coat hanger, and also shopping cart. And in terms of the rod stock, it can be rod stock for nails, screw, rivet, and spring. And for the bar stock, it can be used to make a metal bar for machining, forging, and other processes. For the bar drawing, it is accomplished as single draft operation. So it is different from the wire drawing. So I forgot to mention in the previous slide. Usually, the wire is performed in several steps in order to get the final dimension. But for the bar drawing, you can perform it in a single draft operation. So this the stock will be pulled through one die opening only. So the beginning stock has a large diameter and is a straight cylinder. So this one will require a bash type operation. Here is the detail of the draw die. So the first thing is there is entry. So entry region is where the work material will start going inside the die. Okay. So if you can see, the area here is a little bit round so that it will be easier for the work material to go into the area here. And then there's approach where the cone shape of region where the draw will start to occur. And then we also have a bearing surface. Okay, so bearing surface is where the land where the work material will start to come out. And then we also have back release, where is there is the exit zone where the work material will start to come out. This one will have the angle around 30 degrees to allow for the work material come out easily from the die. And then we also have approach angle alpha over here. So the die material is usually tool steel or cemented carbide. Now we look at a problem on the drawing. Okay, so a spool of copper wire has a starting diameter of 22.5 mm. It is drawn through a die with an opening which is 2.1 mm. The entrance angle 18 degrees. Coefficient of friction 0.08. Pure copper has strength coefficient 300 MPa and strain hardening coefficient 0.5. So the operation is performed at room temperature. They want us to determine the area reduction, draw stress, and also draw force required for the operation. So for A, we have to calculate the reduction. So reduction equation is given by R equal to A naught minus A final over A naught. Since it is already given, the radius, the initial radius is 2.5 mm and the final one is 2.1 mm. So we can calculate the A naught and also the A final here by using the equation for the area. Okay, so this 0.25 is because of divide by 4. Okay, so then um, because of the pi r squared over 4. Okay, so then you'll get the 4.91, and then you can have the final diameter 3.8. The final cross-sectional area is 3.46 mm squared. So when you put it inside the equation, you will get 0.294 as the final R value, reduction value. So the B question want us to draw calculate the draw stress for this operation. Okay, so in the equation it doesn't say that it is a homogeneous or no reduction process. So you have to use the equation given by Shea, where we have to assume that there are friction in the process. So in this process, we have to calculate the way for you to easily see what are the things that you don't have in the equation is you can go to the equation, draw stress 1 plus okay, so all the things is already here. Okay, now we can calculate the epsilon here. So epsilon equal to ln 4.91 is already given here over the 3.46. Okay, and then you will get the strain. Okay, so this is the strain, and then based on this one you can calculate the value here. Okay, so where this is the YF. Okay, the YF equal to 118.2 MPa. Okay, so then this calculation, the next one is this one. So this one is given by this equation. So what you have to do is just you can include it inside the equation, and then you will get the value. Okay, so this one for this D and LC is not there yet. So you have to calculate the D. D is given by 0.5. This one is the initial diameter plus the final diameter. Then you will get this value. And LC is 0.5 times the 2.5 minus 2.1 over sine alpha. So alpha is 18 degree. So you'll get this value. For the LC, then you can put these two value inside this equation. Then you will get this value as the answer. After you already have all the value here, so since this one is given, this one also done, this one also you have, and this one also you have, so then you have to put all inside the equation only, then you will get the answer here. And the final one is the draw force. So draw force is A final times the draw stress. So since draw stress is already there, A final also you already have inside here. So you can just calculate directly and you will get the value 233 Newton. Yeah, so here another question on the drawing process. So try to answer the question before you see the solution. I want you to try before you you look into the solution, so that you will understand on how to calculate the parts. The process is still the same like the previous question, only there are certain information is a little bit different from the previous one. So here are the solution. You can try on your own. Here is the link to video showing the wire drawing and also the bar drawing process. You can see the different, a very clear difference between the wire drawing process and also the bar drawing process in this video. Okay, make sure you look into the video so that you can differentiate between the process. So that's the end for the wire and bar drawing process. Thank you for listening. Assalamualaikum.